Thank you. Okay, so in this problem here, we just have a bunch of reactions starting with a ketone. Did anybody work on this over the weekend? Oh, no? Okay, well, I hope you guys did study over the weekend. I know it was distracting, but we already pushed back the exam 1 week. We can't really do it again. So you're going to take an exam this week. Make sure that you do study and work on this. It's not going to be an easy exam, and there are going to be essay questions. Okay, so if you have a ketone and you react it with a primary amine and acid, what functional group are we going to form?
Is it an imine?
Yes, yeah, it's an imine. So remember that when you're drawing out the structure of your imine, really you're just going to take that nitrogen and that methyl group and you're just going to plop it where the oxygen was. Of course, the mechanism is a little more complex than that, and you should know a good amount about the mechanism. Yes, we are going to make an imine. Also, I know I've been hounding you guys about studying this way, but make sure that you are generalizing. So if you're making flashcards for these types of reactions, you should have ketone plus primary amine plus acid creates imine, right? Generalize using functional groups. Okay, if we have a secondary amine and we react to the ketone, what functional group do we get?
An enamine.
Right. So we're going to make an enamine. This one's a little trickier. There's going to be a single bond between the nitrogen and the carbonyl carbon. We still have a lone pair on that nitrogen. We still have our methyl group. And we have to have a double bond between the alpha carbon and the carbonyl carbon. We have kind of a tricky situation here. We have an alpha carbon over here. We'll call this alpha 1. And here we have alpha 2. Where are we going to make the enamine? Which one is going to create the more stable enamine?
At the alpha 2 position?
I see in the chat alpha 1, and I heard alpha 2. Alpha 1 is correct. Why alpha 1?
It's more substituted.
Right. So remember your rules about what makes an alkene more stable. The more substituted is going to be favored. Okay. Next, we have a ketone. We have a diol. So this is ethylene glycol. And we have acid. What functional group are we going to make?
Acetal.
A cyclic acetal?
Right. So we're going to make an acetal, and it's going to be cyclic. Perfect. I'm going to keep writing out some functional groups here. Okay. Next one, we have our ketone and we have MCPBA. What's the functional group for MCPBA? Because remember, it doesn't have to be MCPBA for this reaction to work.
Does it create alcohol?
No.
Ester.
Whoops. Sorry about that. Yes, we are going to create an ester. This is a peroxy carboxylic acid. So remember, it could be any carboxylic acid that has been turned into a peroxy acid will make this reaction happen. What is this reaction?
Baeyer-Villiger?
Yeah, this is a Baeyer-Villiger reaction. We're going to insert an oxygen between the carbonyl carbon and the alpha carbon. Are we going to favor putting the oxygen between alpha 1 and the carbonyl or alpha 2 and the carbonyl?
Alpha 2.
Oh, what's our migratory aptitude tell us? Do we prefer the more substituted or the least substituted?
Oh, more substituted.
Right, more substituted. So we're going to end up creating an ester that has a 6-membered ring. So it was 5-membered, and we're introducing another member there. And then this is our alpha 1 down there. So when you take your test, if you see a problem like this, you're also going to see this as an option. So you have to be able to know your migratory aptitude, that the more substituted is going to be favored. What's the weird exception? What's at the very top of the chain for migratory aptitude?
Hydrogen.
Yeah, hydrogen. So even though we go for the more substituted or phenyl, so it's hydrogen, phenyl, tertiary, secondary, primary, at our very top of our migratory aptitude is hydrogen. So if we have an aldehyde and we react with MCPBA, we will make a carboxylic acid. So any aldehyde, that is the case. Okay, I'm gonna erase that because it's not part of this particular problem. But. Okay, and then last one, what is this?
Sorry, quick question.
Sure.
On this answer with the ester, did you make a 6-carbon ring, or is it still a cyclopentane? Whatever.
It's a 6-membered ring now because we are inserting oxygen between the carbonyl carbon and alpha 1. So that adds a new member to the ring. So we still have our carbonyl, we still have alpha 1. So there's still only 5 carbons in the ring, but we also had to add a 6th member, which is oxygen.
Okay, so both of these are the answer, or?
Oh, no, sorry. This would be, I was showing you guys that on your exam, since it's multiple choice for all of the reactions, that's going to be an option, is always going to be the wrong side of the ring moving, or the wrong side of the ketone, whatever it might be.
Thank you.
Okay, no problem. So yeah, I'm seeing a lot of correct stuff in the chat. This is an illid. So it's kind of tricky the way that it was written out. It's showing you a double bond between P and PH3, but we know there's also a resonance form for this, right? Where, how do we run out of space? We have a positive charge on phosphorus, we have a lone pair and a negative charge on carbon. So what reaction are we setting up here?
Acidic.
Sorry, what?
Acidic reaction.
Exactly. So this is for a acidic reaction. Okay, and what is this going to do?
We replace the oxygen with the CH2, correct?
Right.
Would it, well, it would be in the Z conformation, correct? But would it really matter in this situation?
No, it doesn't matter in this situation because it's just a CH2 group, so don't have to worry about it.
Okay.
Okay.
So if it was stepwise, like, step 1, step 2, 3, 4, then we would worry about the Z conformation or whatever.
So you would have to worry about the conformation if there was more on here. So right now, if we actually drew this out with all of the individual bonds, these two are just hydrogens, so there is no E or Z. But let's say this were an R group instead, we would have to worry about E and Z at this point.
Okay, thank you.
Okay, any questions about this page? Cool. Okay, this next one, what is this? What's our functional group?
Can you go back really quick?
Sure.
I missed that last little part. Oh, Oh, so since the two hydrogens are there, we don't have to worry. So like when you say worry about E and Z, do you just mean like if there was like another methyl group attached to that, just like making sure which side we're drawing it
Yeah,
on?
so if we had more than just a CH2 group here, our product would favor the Z conformation. And so we would want to make sure that we ended up doing that. So remember, Z means that everything that has the greater priority is on the same side of the alkene, or you could say same side, right? Whatever R group there was would have to be over here if there were something else.
Okay.
Or if there were two R groups, the one with the higher priority would have to be over here. Because this half of the ring is going to have greater priority than this side. Okay, so what is this functional group here in this first problem?
Acetal.
Yeah, so this is an acetal. Oops.
It's gonna break apart.
Right, so we have aqueous acid, so this is going to be a hydrolysis. So this is the last step. If you're using an acetal as a protecting group, you can put it on and then you can take it off. That's kind of the main point of an acetal, is that it can be removed. Otherwise, it wouldn't be a very good protecting group if you had to just leave it on there forever. So what is it going to break up into? How do we figure that out?
Oh. Or you look at the alpha carbon. I mean the substrate.
Yeah, so you have to figure out which carbon is the carbonyl. So yeah, Devin said it correctly in the chat. We're going to have a carbonyl and a diol. So the trick here is to figure out which carbon is the carbonyl. And that's always going to be the one that both of the oxygens are attached to, right? So this is your carbonyl carbon, which means this is an acetal that was made from acetone. Quick question, we call this compound acetone. Is that the common name or the IUPAC name?
Common name.
That's the common name. What is the IUPAC name?
Propanone.
Propanone. Right. So do you think I'm going to ask you about IUPAC naming for aldehydes, ketones, carboxylic acids, and their derivatives on the exam?
Yeah.
Probably.
Yes. And I'm going to ask you IUPAC, and then there's going to be a couple questions where you can give me some common names, and I'll tell you explicitly to provide the common name. And those common names are ones that you know, like, acetone, formaldehyde. Formaldehyde is a common name. And, acetaldehyde. So there are some common names that you guys know. Okay. Oh, I erased the answer because I forgot what I was doing. Okay. So we have acetone, and then the rest of it is going to be the diol that we have to draw out. And that's going to be a 2-carbon diol. Okay. Any questions about how we came up with this? Cool. So again, just if you can identify the carbonyl carbon, you can come up with the carbonyl compound, and then all the rest of it would be the diol or the alcohol, depending on what your acetal looked like. Okay, this next one, we have a ketone and we have a secondary amine. So what are we forming in the first step?
An amine.
Can you say it again?
Enamine.
Enamine.
Yeah. So we are going to form an enamine here. Okay. And where are we going to form the double bond? Do we like alpha 1 or alpha 2?
2.
Alpha 2.
2. Okay. And then we are adding methyl iodide. Oh, that's another common name, right? Saying methyl iodide is the common way of naming this, whereas the IUPAC way is iodomethane. I'm not going to ask you about alkyl halides, but when I use a common name, I should probably point that out. What happens when you react an enamine with an alkyl halide in heat?
It acts like an enol or enolate, and it attaches at the carbocation.
Perfect, yeah. It's going to act like an enolate. Let me draw this out a little more correctly. So the lone pair comes down. We kick out the iodide. Okay, and now we have an iminium ion. What happens when we react the iminium ion with aqueous acid?
Doesn't it turn it into a carbonyl group, or it turns into
Right,
nitrile?
yeah, so you're just hydrolyzing the imine back to the ketone. So basically, this is a fun way of adding on a methyl group. What's the name of this process?
Is the Robinson or?
No, you're a little ahead. That's in chapter 19.
Is it the stork enamine?
Right. So stork enamine synthesis. Cool. Yeah, a couple of you guys guessed correctly in the chat, I see. Which is cool. Okay, any questions about this? Okay, so this one is a little more challenging than what we've been doing. Did anybody work on this? Maybe we should work through the problems and then work through the synthesis one. Let's jump ahead to some problems. Let's get those out of the way, and then we can go back to synthesis at the end. Okay, so let's work on this one. There are a lot of steps. Do you think I'm going to give you a question with 7 steps on your exam?
Yes.
Oh, totally not.
You guys think I'm much meaner than I am, except for Isaiah. No.
Oh, I thought you would. Sorry.
No, I'm not going to give you one with 7 steps. That makes it really, really difficult to figure out how much you got correct, because this is multiple choice on your exam, right? So in a normal semester, when you're doing everything on paper, I give partial credit for each step, but I can't do that in multiple choice. So you're not going to get a 7-step reaction on your exam, but you will get several pieces. Okay, so what's happening in the first step?
We're making a Grignard reagent.
Right. Okay, so we have our Grignard reagent, and then we're adding in carbon dioxide. What happens when you react a Grignard with carbon dioxide?
A carboxylate.
Right. So remember, our Grignard is going to attack carbon, push the electrons onto one of the oxygens, and you end up, that was about to be a really, really bad cyclohexane structure there, benzene. It still wasn't great. Okay. We end up making a carboxylate. Okay, and then in step 3, we're adding H3O+. What are we doing there?
Protonating
the
oxygen.
Yeah, just protonating it. So now we have benzoic acid. Okay. And then we're reacting with lithium aluminum hydride.
A primary alcohol.
Reduction.
An ester?
Sorry, say it again.
Are we not reducing?
Aren't you deprotonating?
Not just deprotonating.
You're getting rid of the carbonyl, aren't you?
Yeah, this is a reduction.
Is
Okay.
it a primary alcohol?
Right,
What is that called?
Yeah. Is a reducing?
Reduction?
right. This is a
Reduction.
reduction. Okay. What is step 5 for?
To
We have 0.1 molar sulfuric acid.
solution.
Right, we are just protonating it. Okay. What is step 6?
Oxidizing. Is it gonna
Oxidation to a
alcohol?
aldehyde.
Right, so Swern oxidation is mild. So we're going to get an aldehyde. Yes, there are ways to go from a carboxylic acid to an aldehyde without reducing and oxidizing, but it's my problem to make as many steps as I want. Whoops.
I think this is why we thought we would see this on the exam. Because of that statement right there.
Practice. Like, it doesn't matter if you messed up on step 4. On the test, it does. So, thanks for the vote of confidence. Okay, so we have another phosphorus ylide happening here. So what are we doing?
Attaching that to the carbonyl.
Attaching
And
it
the
to
Z.
the aldehyde.
Oh, come on. Stop it. Yeah, so this is a Wittig reaction. So what? Sorry, I think it's because in order to draw right here, I'm having to rest my hand like at the bottom. Okay. Sorry, it's gonna look a little wonky because I can't rest my hand on here. So we are creating a double bond to a carbon. Am I gonna draw my carbons to the left or to the right?
To the left.
We're doing to the left.
Yeah, left.
Right. So there's a hydrogen here. Okay. Cool. And this is because the Wittig reaction favors the Z product. So answering a question in the chat. What is our other reaction that kind of does the same thing? What's it called?
The Bayer.
The Horner Wadsworth.
Yeah, it's the Horner Wadsworth
Sorry.
Emmons. You don't have to apologize to me. It's not my last name.
Know that guy.
Yeah, so this one is going to favor the E. So if we had used a phosphonate ester instead to accomplish this, we would have to draw it the other way. And that uses the phosphonate ester.
Sorry, just so I'm verifying. So when you say the Horner, whatever this dude's name is, it refers to the E conformation. So pretty much you'll still see PPH3, or is it
that's the one that uses the phosphonate ester.
Okay. Oh yes, that's right. Okay, thank you.
Like a big one.
I feel like we saw a couple of these and I forgot. Thank you.
Yeah, it's just those two. Yeah, so just a phosphorus ylide like this is Wittig, and then the other one has your phosphonate ester. Okay, so for this one, the Z is the product though. So I'm gonna erase Horner Wadsworth Emmons here. Okay. Any questions about this? That got really fun really fast, right? Great.
I like this one, probably because I knew all of the reagents.
Okay, let's do another many stepped reaction. So what time is it? Okay, it's 10:30. Let me see. I can't remember how many problems we have. I think this is the last page here. Okay. So I'm going to go ahead and put you into breakout rooms. So go ahead and write this one down. This is also available on that PowerPoint that I asked you guys to download. And I do want you to go ahead and work on the last page also. So I'm not going to give you time to like copy this down right now. So take a picture of it or whatever you need to do. But I want to put you guys into breakout rooms for about 10 minutes. And Anne, I already made you a co-host, so you're good. Anne and I are going to hop around. I'm going to give you 10 minutes. So make sure that you are working on this. We're going to check in all the rooms.
Can you go to the other problem?
Yes. Remember, these are on Canvas, so you can take a look at them. Okay, and if you end up stuck in a breakout room where nobody's talking or something, leave it and let me know so I can reassign you and check on your room. But Anne and I are gonna hop around. So. Okay, you can go there when you have everything written down.
Can you go back to the last one real quick? I just need a number 7.
Sure.
Dr. V, before I go into the room, I had a quick question about this actually. This is
Sure.
So NaH, I learned that it's non-nucleophilic, so it would be the kinetic product. Is it when we're doing the enolate synthesis, is that correct or is it thermodynamic? Because one of the students was like, oh, it's thermodynamic, but I learned it was non-nucleophilic, so I said, okay, it's kinetic, non-nucleophilic, but
yeah, no, I would call it kinetic.
okay.
Yeah, I agree with you.
Okay, cool. Yeah, somebody asked me about it, and
yeah, I don't think I used it to make enolates, so I'm not even sure that we talked about it in class. Did we?
Okay, yeah, because I had it. Dr. Allison used it a lot when I took it for that class, and so I was like, oh, it's. And somebody else said they looked it up, and they were like, it's kinetic, thermodynamic, and I was like, oh, I don't know, but yeah, okay, cool.
Yeah, I don't know. We haven't used it, so I don't think I will either. I don't usually.
Okay, thank you.
Okay. Everybody. I want to thank you all for working in the breakout rooms. It's actually really fun to hop around and like hear you guys talking about this. So let's try and get through as much as we can, and then whatever we don't finish, I'll record myself going through after class, and then I'll post it for you guys. Okay, so in step 1, we have sodium hydride. So what is sodium hydride used for sometimes?
Deprotonation.
Yeah, it's a good base, right? So we can use it to deprotonate our phenol. So that gives us phenoxide. And then we add in methyl iodide. What's going to happen?
I'm
gonna create an ether.
Right, the SN2 reaction. Does anyone happen to remember what the name of this reaction is from OCHEM 1?
I think it's the Williamson ether synthesis.
Yep, exactly. Williamson ether synthesis. Okay, in step 3, we have our ether. What is the name of this compound, by the way, the accepted name?
Acyl chloride?
Sorry, what we made in step 2.
Oh.
Ooh, we forgot our aromatic names. Flashcards.
Is this
Yeah.
the one? Oh.
It's the anisole.
Yeah, make an organic flashcard deck and go through it like once a week at least, especially since you have a final exam coming up with all of OCHEM 1 and 2 on it. Okay, so in step 3, what is this compound here?
Acyl chloride.
Acyl
Right.
chloride.
And AlCl3. So what are we setting up here?
Crafts acylation.
Right, a Friedel-Crafts acylation. Is the methoxy group an orthopara director or a meta director?
Orthopara.
Orthopara.
Orthopara. So let's go ahead and just draw the para product and just move forward with just one. So step 4, what is that?
Grignard reagent.
A Grignard. So what is it going to do?
Attack carbon and push the electrons on the oxygen.
Right.
On the ethyl too.
Right, so this would create an alkoxide. Let's go ahead and do steps 4 and 5 together so we're not drawing out the structure multiple times for no reason. Step 5 is just to protonate it. Okay, so we have a tertiary alcohol now, and we add in PBr3 and pyridine. What are we going to make?
An alkyl halide.
Right, so this is going to take your hydroxyl group and replace it with a bromine. This is essentially the bromine equivalent of thionyl chloride. Okay, and then we add in T-butoxide, potassium T-butoxide, and T-butanol. What are we doing?
Isn't this just an SN2 reaction?
Not SN2 because this is pretty bulky.
Oh, it is SN1.
Aren't you replacing the bromine with the oxygen?
No.
Oh.
What happens with a bulky base and a tertiary alkyl halide? This is OCHEM 1, so it's kind of mean.
Elimination reaction?
What? I'm sorry?
And E2?
Yes, this is E2.
Oh, it is E2. Okay. I knew it was a strong.
I was like, elimination?
I always mix those two up.
So we are taking out bromine. Just make sure that you draw the most substituted one. Okay. Did I see that a lot of you guys got pretty close, or you got it? That's awesome.
We got all the way to 7, and I mixed it up by saying it's SN2.
And then, Justin, I see your question. Does it matter if the ethyl is on the side and methyl in the middle, or vice versa? No, I just drew it that way because it's easier, so I didn't have to try and shove the ethyl group somewhere. Okay, so it's 10:52. We are out of time. So if you need to leave, you can. I have office hours today at 12:30. And I do have to go right now. I have to go check on my labs. But at 12:30, I'll do office hours. We can finish going over some of these problems if you want. And then I have office hours on Tuesday from 10 to 12 or something like that.
I just have one quick question about step 4. Did we just, I guess it's just one of those things we just know after we make that anisole, we should just know that it goes into the pair position because of that Grignard? Like, okay, so like when I did it, I don't know why I thought that that ethyl was going to attach and replace, like, I don't know what I thought was happening. Somehow
So the pair position stuff is decided in step 3. I'm not sure I understand your question.
Okay, yeah, sorry, step 3. So that I confused myself with that question. What I meant was, okay, so we form the anisole and then step 3 comes, and then I know that it's acyl chloride, but I guess at some point, the way I did it, I was thinking it just replaced the anisole and then the acyl chloride goes in that same position. Like,
Oh, okay. No,
does
so
that make sense?
yeah, I understand. So
Which I don't know why I thought that. I guess I just didn't
yeah,
think
so
about.
nothing's going to happen to the methoxy group. It's just going to direct the outcome of the reaction. So that has to stay there.
Okay, so anisole is just like one of those that are kind of stuck the way it is.
Well, so for any electrophilic aromatic substitution, you're not going to be replacing that group. So this is an EAS reaction. I think you're thinking of NAS.
Oh, okay, that's probably why.
So for the nucleophilic aromatic substitution stuff, you really can only displace like a halide from a benzene ring. And that's going to be using either hydroxide or azonide. Like those are your 2 situations. And you have to have an alkyl halide. And it also needs to have some sort of electron withdrawing group on the ring as well.
Okay, so that was if it was NAS.
Right, yeah.
Okay,
So
all right.
a very specific situation.
Okay, thank you.
Mm-hmm. Okay, so hopefully I'll see a lot of you guys at 12:30. And Anne is saying that she has office hours Wednesday at 2 p.m. So if you're not taking the test with me, you're taking it on Examity, you can still ask questions at 2 p.m. Or you can go there just for general studying.
Dr. B, I have a question.
Sure.
I know I asked you earlier, like in this, after we did exam 1, if exam 1 responses would be released.
They were released a while ago on Canvas.
Because every time I checked, it keeps saying that my exam still needs to be graded.